In this video, we're going to talk about one of the key applications of the calculus that we've learned so far, or optimization. So optimization problems are problems that involve finding the absolute maximum or minimum of some function. Now, these problems can be very, very complex, and we're going to just sort of scratch the surface of them. One of the problems we'll do in class, we'll talk about how it extends and things to think about. So common optimization problems that we'll see are maximizing revenue and profit, inventory control, and minimizing the variance of investment portfolios. I guess another one would be maximizing the Sharpe ratio of investment portfolios. So the last two, the minimizing variance and the maximizing the Sharpe ratio, are going to be topics for next week. Okay, so the best way to do optimization problems is really to practice, to do some examples, to think about how they work. Our first problem is about maximizing revenue. So we have an office supply company. They sell X permanent markers each year at a price P dollars per marker. The price demand equation is P equals 10 minus 0.001X. What price should the company charge for the markers to maximize revenue, and what is the maximum revenue? Okay, so revenue is P times X, which is P was 10 minus 0.001X, so we multiply that by X, and we get, as we'll write it all out, 10X minus 0.001X squared. Now, price and quantity must both be positive. So the domain for revenue is 0 is less than or equal to X is less than or equal to 10,000. Right, if we plug 10,000 into this equation, into our price demand equation, we get a price of 0. So to solve this, again, we've got a closed interval for X, so X is between 0 and 10,000. So what we need to do is find the critical numbers, check the revenue at the boundaries of the domain, and check any critical numbers. The one that gives us the biggest revenue, that's our absolute maximum. The one that gives us our smallest revenue is our absolute minimum. Okay, the derivative of revenue is, take the derivative of our revenue function, 10 minus 0.002x, right? X squared becomes 2x, multiply 0.001 by 2, 0.002. So that's our derivative. There's a single critical number at 5,000, right? 10 minus 0.002x, 5,000 gives us 0. So we've got a single critical number at 5,000. The revenue at the boundaries and the critical number are, well, if we plug 0, we sell 0 items, revenue is price times 0 is 0. And if we sell 10,000 items, remember the price was 0, so we get 0 times 10,000 equals 0. So at the boundaries, the revenue is 0. When the revenue is 5,000, the revenue is $25,000. So we check both of them. This is our absolute minimum, and this is our absolute maximum. Okay, so there's an absolute maximum of revenue of $25,000 when the company sells 5,000 markers for $5 each. If we want to maximize profit, so say the previous company has a cost for manufacturing markers of $5,000 plus 2x. So $5,000 fixed plus $2 per marker. We want to find what is the company's maximum profit. What should the company charge for each marker, and how many markers should they produce? So now we're doing a slightly different problem, but it's similar, right? The profit function is P of X equals R of X minus C of X, revenue minus cost. P of X is 10 minus 0.001X squared minus 5,000 plus 2X. And I guess we should rewrite that. So P of X equals negative 5,000. We've got a 10x plus 10x minus 2x, so that'd be plus 8x minus 0.001x squared. So negative 5,000 plus 8x minus 0.001x squared. The domain for the profit function is the same. Costs are always positive, whatever number of pens we create. Again, we want positive prices and positive quantity, so quantity must be bigger than 0 and less than or equal to 10,000. To solve, same problem. Find the critical numbers, check the profit of the boundaries of the domain, and any critical numbers. Okay, the derivative of profit is 10 minus 0.002x minus 2, or 8 minus 0.002x. There's a single critical number at 4,000 pens. So we check. The profit of the boundary, profit at 0 is negative 5,000. Profit at 4,000 is $11,000. And profit at 10,000 is negative $25,000. So this one is our absolute min. We certainly don't want to do that. And this one must be our absolute max. So to maximize our profit, we produce 4,000 markers, sell them for $6 each. That comes from our price demand equation. And the profit is $11,000. So strategy. Set up our equations. Figure out what the domain is for those equations. What are the reasonable values for those equations? Solve for critical numbers. Take the derivative, set it equal to 0, and then calculate the value of the function at the boundaries and the critical numbers. So one other problem. So this comes up frequently. Inventory control. So a company anticipates that there will be a demand for 120,000 widgets during the next year. It costs the company 50 cents to store one widget for 1 year. And each time it must make additional widgets, it costs $1,875 to set up the equipment and $1 to produce one widget. How many widgets should the company make during each production run to minimize its total storage and setup costs? So the assumption here is that this company is going to sell widgets constantly throughout the year. So every day they sell 120,000 divided by 365 widgets. Okay, so the basic assumption, demand is uniform. We also assume storage costs are proportional. So if it costs 50 cents to store the widget for a year, it costs 25 cents to store the widget for half a year. It costs 12.5 cents to store it for 3 months, and so on. Okay, so I find this easiest to think through some examples and then figure out what happens. Once I've figured out some examples, I can put together some equations. So right now we're missing our equations. So first example, let's say we made all 120,000 widgets at the beginning of the year. Production costs would be $18.75 plus 120,000, remember $1 per widget. The storage costs would be 120,000 times a half, or 30,000. Now, we've got to think about this. Okay, each widget on average is going to be stored for approximately half a year. Why is that? Because you can look at your widgets, look at the first widget you sold and the last widget you sell. The first widget you sell isn't stored at all. The last widget you sell is stored for an entire year. Together, they're stored for, on average, half a year. If you look at the next two widgets, one's stored for a very short period of time, the other one's stored for almost a year minus that short period of time. On average, they're stored for half a year. So the storage costs are 120,000 times 50 cents, which is the cost of storage for a year, times a half, or $30,000. Total costs would be production plus storage, or 151,875. Let's do another one. Let's say we did 10,000 widgets every month, the beginning of each month. So production costs now are $18.75, the setup costs, times 12, because you did this 12 times, plus 120,000. 120,000 is how many widgets did we produce? $1 each. Storage costs now are different, right? So let's just think about a month's widgets, right? We produce 10,000 widgets. It costs 50 cents to store them for a year. They're only going to be stored for at most a month, so we divide that by 12. And we multiply that by a half because, again, of the 10,000 widgets, the first one that's sold is stored no time. The last one that's stored is stored for an entire month, on average, half a month. So 10,000 times a half, which is the 50 cents, times a half times a 12th. That's how much it costs to store. Of course, you do this 12 times, so it costs $2,500. Total cost now would be $145,000, right? The $142,500 from production plus $2,500. If you look at these, right, production costs are going up. Storage costs are going down. Okay, storage costs is the hardest part. If we do Y production runs of 120,000 divided by Y widgets, then we do a production run every 1 over Y years. On average, the widgets we produce are stored for half the time, so the storage cost equals X, number of widgets, times storage cost, times a half, times 1 over Y per run. Okay, so we're going to take this X times this stuff, and we're going to multiply by Y. So let's define some variables. X is going to be the number of widgets made in each production run. Y is the number of production runs. We write down the equations relating them. So X times Y equals 120,000. Cost is 1875 times Y, so 1875 times number of production runs, plus we produce 120,000 widgets, so 120,000 times 1, plus Y times X times a half times 1 over 2Y. Or 1875Y plus 120,000 plus 30,000 divided by Y. Okay. And basically, you can see here you have Y times X. Y times X is 120,000 times a half divided by 2, 30,000. So that's where this equation comes from. It's worth spending a little bit of time working through these equations, thinking about where do they really come from. Okay, number of production runs has to be between 1 and 120,000. It seems reasonable to assume that a single production run must produce at least one widget. So we're not going to have more than 120,000. You've got to have at least one production run. So we want to minimize cost relative to the number of production runs. So what's the process? Take the derivative, find the critical numbers, evaluate the function at all the critical numbers and the boundaries. So we take the derivative, 1875 minus 30,000 times y squared, 1 over y squared. Find the critical numbers. Y equals plus or minus 4. Minus 4 doesn't matter. The only one that we care about is y equals plus 4. And then we check costs. Cost of one production run, 151,875. 4 production runs, 135,000. 120,000 production runs, $225 million. So the 225 million is our absolute max. 135 is our absolute min. So we want to do 4 production runs per year, minimizes the cost of production at 135,000. It is worth reviewing this part of the video a couple of times just to make sure you've got the hang of how to do these inventory control problems. There is another example on the Canvas page.